Hour is Professor Matsuno from Yamaguchi University, yes. And you'll speak about the Camassa-Holm system of equations. Please.
Thank you for the introduction. First, I'd like to express my thanks to organizers of conference, Professor Constantine and Professor Okamoto, and also thanks is given to the Isaac Newton Institute for various support. First, I apologize that because of my speaking in English, I speak very slowly. So, if you have any question, please speak slowly. Okay? Now, this is the outline of my talk. The introduction is concerned with a brief summary of the strongly nonlinear models, which include the Green-Naghdi and related equations. And then I shall develop the exact method solution for two-component Camassa-Holm system. And then I examine the properties of soliton solutions. Then I like to explain deduction of the Camassa-Holm two-component Camassa-Holm system to integrable system. Last, I comment on probably interest issue concerning the p-cons for the Camassa-Holm and related equation. I conclude my my lecture by brief summary. Now, here, I'd like to review model equation for strongly nonlinear shallow water waves. Here, first, the extended Green-Naghdi models. Now, basic assumptions in deriving model equation is first, two-dimensional irrotational flow of incompressible and inviscid fluid of uniform depth. Second, the effect of surface tension is neglected, which is usually valid for usual water wave. Yeah, this is a configuration. Now, the governing equation of the water wave problem in terms of the dimensionless variable is, this is the continuity equation, or Laplace equation here. Here, phi is the velocity potential, and eta is the surface profile here. And the second equation is the kinematical boundary condition at the fluid interface. And third one is the dynamic boundary condition or Bernoulli equation, which holds at the fluid interface. The last one is the bottom boundary condition. Okay. Now, there exists two dimensionless parameter in the system under consideration. The first one is the nonlinear parameter epsilon A over H0. Second one is the dispersion parameter, which is H0 over L. Here, A is the typical amplitude of the waves, and L is the typical amplitude scale of the waves, where the wavelength in the case of periodic waves. HL is the mean depth of the fluid. Here, the configuration is okay. Now, there are several strongly nonlinear models. Among them, the Green-Naghdi model is very famous, but it incorporates of the lowest order nonlinearity. Okay, so recently I have derived the equation which extends the Green-Naghdi to include the higher order dispersion here. Here, there's a system of equations of H and U bar. U bar is the mean horizontal velocity component defined like this, okay? And h is the total depth of the fluid, and km is the function of h and u bar and the x and t derivatives. So it is important that this equation is exact equation without any approximation. This merit, because if we use this quantity, then this becomes exact. But of course, this is approximate equation, which take into arbitrary order of dispersion. Okay. Now, this equation derived from the simplest configuration, the flat bottom topography, and the flow is two-dimensional. Quite recently, also, I extend this system to three-dimensional flow with an uneven bottom topography here, okay, where I discussed the linear dispersion relation of this system. Okay. Now, there are several simplified models arising from the Green-Naghdi and the equations. First one is the classical business system, which can be written like this, where epsilon and delta scales the same orbital and is small compared to 1. The second equation is the Green-Naghdi system, which is famous system of equation. This equation has been derived probably for the first time by Serre in 1953. But unfortunately, his paper is written in French, so that most people did not notice his important paper. Subsequently, in 1969, Seward Gardner derived this equation from the basic Euler system. And Green-Naghdi extended this system to three-dimensional flow and with an uneven bottom topography. So this equation, sometimes called the Serre equation or Serre-Gardner equation or Green-Naghdi equation. Green-Naghdi equation may be most popular. Okay. Surprisingly, this system has exact solitary wave solution like this. This type of solution, exact solution, does not exist in the classical business system. But this solution itself has been obtained in almost 140 years ago by Lord Rayleigh by a different method. Now, as you said earlier, the Green-Naghdi system incorporates the lowest order dispersion so that it can be applied to very shallow water phenomena. There are several extensions of the Green-Naghdi system to include the higher order dispersion. A number of papers have written about this, but since this is another story, which I do not address here. Now, the equation which take into account the force power of delta is here. Okay, delta 4. In addition to delta scale term, we have the force power of delta on the right hand of the equation u bar. Okay, but to my knowledge, nobody studied this equation as yet. But this equation is very complex because higher order derivatives contained here. Importantly, the system 1.7 and 1.8 has the same Hamiltonian structure. Okay? So that, of course, energy preserved. Also, mass and momentum is also preserved. Now, we're going to explain the two-component Camassa-Holm system, CA2 hereafter, and its deduction. Now, the CA2 system can be written as it is a system of equations for U bar and or U and rho. Rho is defined by this. It includes eta in addition to U. M is something called the momentum density, which is defined by this equation. And at the lowest order, rho is almost, rho minus 1 is almost eta. Eta is a surface profile. This are there are several features, characteristics of the system. First, it's a completely integral system. Namely, they have Lux sphere, bi-Hamiltonian structure, an infinite number of conservation laws, and so on. This fact has been obtained by Oliver and Rosner in 1996 by Hamiltonian formulation. Now, this is a model of shallow water wave, which can be derived from the Green-Naghdi equation. This is Vidal constant and Ivanov in 28. Also, Ivanov derived the similar equation in 29. And it has the it exhibits the wave breaking phenomenon. Wave breaking means that the wave profile becomes slope becomes infinite, but the wave height remains constant value. It is called wave breaking. And but this system does not have the Peakon solution. Now, as you know, there are several exact methods of solution for solving the nonlinear, integrable nonlinear wave equation. No? Now, applications, probably inverse scattering method is most popular is method of solution. In fact, Holm and Ivanov applied this method to two-component Camassa-Holm system. Then another one is the direct method here, which is initiated by Professor Hirota in 1971. And this method is very powerful in constructing soliton solutions or periodic solutions. I have used this method for a long time, and also in my talk, I use this method and to obtain the soliton solutions of the C2. Unfortunately, Professor Hirota has died a few years ago. Now, there are several variants of the C2 system. The first one is also almost similar to the C2 system, but please note that the sign of the here is minus. In the case of C2, it's a plus. Okay. But this, I think, this is a big difference because this system exhibits Peakon solution, and it can be derived from the basic Euler system with an upward constant acceleration of gravity, so that they may be unphysical. I don't know the physical phenomena that this equation is applicable. Okay. Now, another one is non-local modification. Actually, if one replaces rho x here by a non-local operator, this is a convolution integral here. Okay. This system exhibits Peakons, okay, but it will not be completely integrable. This system has been proposed by Holm and others in 29. But I don't know any physical situation for which this system is applied. But maybe mathematical model. Now we are going to explain the reduction of the CS2 system to various integral systems. As you know, CS2 system is completely integral. Then the several reductions to completely integral system. Here I show schematically the reduction process. Here CS2 is here, and we obtained the Camassa-Holm by scaling limit. I explain this scaling limit later. And then applying the short wave limit to Camassa-Holm, leading to the Hunter-Saxon equation. Another way is that CS2 applying the short wave limit to CS2, then we obtain two component Camassa-Holm two system, and then applying this to scaling limit to Hunter-Saxon equation. There are two different avenues leading to Hunter-Saxon. Of course, we can obtain the same result. Now, I explained each equation shortly. The Camassa-Holm equation can be written like this. The famous shallow water model equation, but actually this is a single equation for U, but usually one introduce the quantity m. Here kappa is a dispersion parameter, okay? Dispersion parameter here. This equation has been derived Camassa-Holm in 1993 from the water wave problem. But this equation has been already derived by purely mathematical point of view. And a number of work been done for the Camassa-Holm equation. Now, two component Hunter-Saxon is here. The difference between the Camassa-Holm 2 and the Hunter-Saxon equations is the expression of m here. U is lacking here. But also this is in completely integral system. Finally, Hunter-Saxon equation stems from this by simply taking rho is equal to 0, and this system turns out to be the single equation for U. Usually, when the kappa is not absent, this system is called the Hunter-Saxon equation. But in my talk, we include the parameter kappa. This is a Hunter-Saxon equation itself is model for propagation of weakly nonlinear orientation waves in pneumatic liquid crystal, director field, which has been proposed in 1991 by Hunter-Saxon. There are also the many works concerning the Hunter-Saxon equation. Now, the purpose of the present talk are construction of multisoliton solution of the CS2 system by means of a direct method. Okay? Second, investigating the property of the soliton solution. Third, reduction of the CS2 system to integral system mentioned above. This last one may be interesting. I remark on P-con for the Camassa-Holm and the related equation. All equations mentioned here the P-con solution. But I like to show that in some cases, smooth solitons recover the P-cons in some special limiting procedure. Now, I like to developed the exact method of solution. The maybe technical detail may be tired for almost on this audience, so that I outline results only. Usually, Camassa-Holm and related equation is difficult to solve when compared with the Korteweg-Debris equation, because the solution has a parametric representation. So usually we use the equation to transform another one by introducing reciprocal transformation. It's usually sometimes called the holograph transformation, which is family in the theory of water waves. Now, reciprocal transformation from xt to yt are given like this. Idea is how to derive this equation is that here the local conservation, we are focusing the local conservation law. It follows from this that we may introduce this transformation, so that the x and t derivatives are rewritten in terms of y and the tau derivatives by this relation. Now, applying the 2.1 to CH2 system, we obtain the system PDE here. This is equivalent to the original CH2 system. Okay. It follows from this equation that x is the dependent variables of y and tau obeys the system of linear PDEs here. Okay. This system equation is integral since its compatibility condition here is assured by virtue of the original basic equation. Okay. Now, the quantity here can be written in new coordinate system like this here. Sorry, the subscript tau and y denotes the partial derivative. Okay. Also, the partial derivative of tau. Y is partial derivative. Tau is partial derivative. And so, at this stage, let us introduce new independent variables y, capital Y, the function y and tau by the relation here. Okay. Substituting this expression into 2 point here, and integrating the result by y under the boundary condition here. Yeah, boundary condition rho is rho 0. Rho 0 is assumed to be a positive constant, non-zero positive constant, which is consistent with our physical setting. So rho can be written in terms of y. Now, then we have two dependent variables, x and y, which satisfies the system PDE here. But this equation is simple, but this equation looks like something complicated here. And proof is very simple. To derive this equation is very simple, because this equation follows immediately from 2.3a and 2.6. That's very easy to derive. But this equation is somewhat complicated, because if we substitute m from 2.5 here, I introduce this expression to here n, and use equation for sorry, and combine equation something like that, and finally we obtained this equation. This is a straightforward computation, and dividing this expression by xy and using 2.7, we obtain 2.8. Okay. Now we have deduced our basic system of equation, or system of equation for x and y, but this looks like very complicated system of equation, nonlinear PDEs. Now, bilinearization. The essence of the bilinear direct method is transform the given nonlinear equation to bilinear equation through dependent variable transformation. Okay? In the present case, we introduce the dependent variable transformation like this. This is x and this is capital Y, where f, f tilde, g, and g tilde are tau functions, and these an arbitrary constant. Then we establish the following proposition. Consider the following system bilinear equation for these tau functions 1, 2, 3, 4, where the bilinear operators are defined by this equation. Okay? Then the solution of the system of equation solve the equation 2.7 and 2.7. 2.7 and 2.8 is a basic system of this equation. Okay. Thus the problem is reduced to solving the system of bilinear equation here. Now we have a main result in my talk. The two-component Camassa-Holm system admits a parametric representation of the solution like this. U, rho, and x. X the coordinate, of course. Here, logarithmic derivative of tau function like this. This is the main result, one of the main results. Also, we can get the expression of 1 over rho and m over rho square in terms of basic tau function like this. Now I'm going to solve the bilinear equation here. As I said, this method is very powerful in obtaining the soliton solution. Like, of course, special solution, but very powerful for this. Now, in the present case, f tau function can be written in the finite sum like this. Here, besides j is the phase value of the j soliton, like this. And E gamma JL is the interaction coefficient. And psi j and phi j and psi j is parameters, which is given in terms of kj and cj. Cj is a velocity. Okay? Kj is a wave number. And Cj is the velocity of J soliton in the y tau coordinate system, which is given by the solution, the quadratic equation here. Okay. The kj and yj are arbitrary complex parameter in general, satisfying condition like this, and the notation sum mu equals 0 and 1 implies summation over all possible combinations of the mu1 equals 0, 1, mu2 equals 0, 1, and the mu(n) equals 0, 1. In any case, this tau function is expressed in the finite sum, not infinite series. Infinite series appears when construct the periodic solution, but which I do not address here. Now, before studying the properties of solution, I'd like to examine the characteristic of the velocity of the soliton. Of course, this comes by solving this quadratic equation here. This solution. The epsilon j is either +1 or -1. So we have two velocities, different velocities. So, of course, we are concerned with real quantity, so that one must impose conditions for the parameter kj. Actually, one imposes that this term inside of square root should be positive, non-negative or non-negative, so that here, if rho 0 kj lies within this interval, then solution become real quantities. This is a schematic of the velocity as a function of rho 0 k. C plus is here epsilon is +1. Okay, C plus. If epsilon j is -1, it's C minus. Then C plus has a form here. It has singularity at rho 0 k is equal to 1. But the C minus is a continuous function of rho 0 k. This is dispersion relation of soliton. It's a very important feature of the solution. Okay. Now, we're going to explain the properties of soliton solution. Maybe one soliton solution may be most important. So, I obtained one soliton solution, explicit one soliton solution. But of course, this is a parametric representation of a solution. U and rho here. X, capital X is a traveling wave coordinates. Okay? It is very convenient in discussing the one soliton solution, because in this coordinate system, the soliton wave becomes stationary. And the phi and psi and parameter phi and psi functions of the kappa, rho 0 k, and c constants. Now, I'm also interested in the smooth solution, because we are also interested in the physical phenomenon. So that this means that I have already introduced the reciprocal transformation to assure the smoothness of solution. The map 2.1. 2.1 is the reciprocal transformation becomes 1-to-1. In the case of y derivative of x is positive, then the solution is smooth and non-singular. Here, this is a condition. So, okay. Now, finally, amplitude velocity relation is another important feature of the soliton. A rho is the amplitude of rho measured from the constant level, which can be like this here in terms of the velocity c tilde. C tilde is the velocity in the original xt coordinate, and u is the amplitude of mean velocity, which can be like this. So I like to remark that A rho is always positive. This means that wave profile here is of bright type or elevational wave of elevation, which is constant, consist with observation, namely depression wave over dark soliton does not exist in the shallow water problem. Now, this example of the profile of the U and rho. The first one is the profile, the C plus, velocity C plus positive. Then this is a profile of rho, and this is a profile of U. And second one is B, it's C plus, but the negative value. Also C plus also take a negative value. In this case, I take minus 1.25. Then profile is positive, but the mean velocity is negative. So that this soliton propagate to left. Last one is C minus here, also, but similar to this. Okay. Profile positive, but the velocity is negative. So that's a wave propagate to the left. Now, oh, I'm sorry. I speak the general n-soliton solution. Sorry, but we omit the detail of the n-soliton solution, where n is the arbitrary positive constant. Here, asymptotic state is the superposition of n independent solitons, and the pairwise interaction occurs among interaction solitons. This is common feature to all integrable soliton equations. And two soliton cases here. As I said, both soliton can propagate to either left or right. So that's the collision occurs, overtaking collision and head-on collision occurs. Here, the total effect of collision is only the phase shift, which here is the formula of phase shift for right traveling waves. This shows that the graph of head-on collision. The big one right, the small one left, and then this instant collision, and then after lapse of time, both solitons separated and recovers original shape. And this is head-on collision as well. Here, right going soliton, here left going soliton. This is instant collision, and then separate completely and recovering the original shape. This is obviously elastic collision. Now we are going to explain reduction to integral equations, as I said in the introduction. Now, first, I like to explain how the CO2 system reduced to Camassa-Holm system by taking the limit rho z tend to 0 under the scale here. But the scaling here, you should know that scaling of x and t has not been done with the same variables. This is the point. So we can expand all the quantities, velocity, the this is a parameter, empowers rho 0 and retains the lowest order terms in rho 0. And so we obtain expression like this. And this is a form of the tau function like this. G is given like this, empowers rho 0 here. G is expressed in terms F0 here. Okay. So, as a result, we obtain the parametric representation of the n-soliton solution like this. Okay. This is very well known result. Maybe this result has been derived probably almost 10 years ago. Then one soliton solution has a form like this. Okay. Also, by linear equation reduced to this system of equation, but I don't explain this. Now, we're going to reduction to Hunter-Saxon 2 system. Okay. Here, two-component Hunter-Saxon system stems from the short wave limit of the Camassa-Holm 2 system under the scaling. Future is that coordinate x is scaled by epsilon and time t is scaled by 1 over epsilon. So that the new variable x hat is describes slow scale, and tau hat, t hat is a slowly varying variable. Usually this scaling called the short wave limit in the literature. Now, CS2 system reduced to this Hunter-Saxon system under this scaling. And also the soliton solution, to obtain reduce the soliton solution, one into this scaling and something like that. Okay, so that the tau function is expanded like this, and here finally one obtains the parametric representation of the n-soliton solution like this. Okay. Now the one soliton solution can be written like this. Also, by linear equation can be reduced to this equation. Please note that P-con exists in this system when kappa is 0 and rho 0 is 0. Rho 0 is the boundary value of rho. This fact has been shown by Konstantin and Ivanov. Now, last is the reduction to the Hunter-Saxon equation. Now, we omit the detail, and we can obtain the parametric representation of the system like this in terms of a single tau function like this. Now, this is the parametric form of the one soliton solution here. This is the form of the cusp soliton. Cusp means that this profile, the slope of the profile becomes infinite at the crest. It is not different from, it is different from the P-con, something called the cusp soliton, because singular solution. Now, finally, I like to remark on P-cons for the Camassa-Holm and relating equations. Okay. As I said, several equations has P-con solutions, but my concern is the transition from the smooth soliton to P-con by taking an appropriate limit, which called P-con limit. Okay. which I define zero dispersion limit with the velocity of the soliton being fixed. Namely, I like to kappa 10 to this is zero small dispersion limit. At the same time, one must take kappa k 10 to 1 because this is the expression of velocity here. This is Camassa-Holm and modified Camassa-Holm equation like this. This is a Degas-Paris process equation. Last one is the Novikov equation or the integrable equation. So if I turn kappa 10 to 0, at the same time one must kappa k 10 to 1 to fix C. Okay? This I call the P-con limit. So my question is, do smooth soliton recover P-cons in the P-con limit? Okay. Now, in the case of Camassa-Holm equation, it is P-con solution. P-con solution is when kappa 0 exists here. Okay, and this figure shows the transition from the smooth soliton to P-con solution. Here the smooth soliton, the value of kappa k 0.5, and this dotted curve here is almost P-con when kappa k is 0.8, and last kappa k 0.99 here. This is a P-con solution. So that in the case of Camassa-Holm, the smooth soliton recovers P-con in the P-con limit. Now we have the Degas-Paris process equation, which is also a very important equation, but its mathematical structure is very different from the Camassa-Holm equation. Here the coefficient is 3 and 1. In the case of Camassa-Holm, the coefficient 2, 1, 1. Okay, but compared with Camassa-Holm, to my opinion, this is very difficult to analyze. Okay. Now this equation is the P-con solution. This same form as the P-con, the Camassa-Holm equation. Also, we can obtain the similar graph, so that in this case, smooth soliton recovers the P-con in the P-con limit. Now, Novikov equation is another integral equation. Here, unlike the Camassa-Holm equation, this is third cubic nonlinearity here. Okay. This equation has been derived by Novikov from the mathematical point of view. So, soliton solution exists under the boundary condition. We impose a non-zero boundary condition, so that we can obtain the general multisoliton solution. I show this in this paper. Now, also P-con solution exists when exists. In this case, kappa is defined like this, so that when kappa tends to 0, here, this is the smooth soliton. Then here, last one is the P-con, like this, P-con solution. Now, last one is the modified Camassa-Holm equation, which will be most interesting among other equations, because we have a modified Camassa-Holm equation. Here, like this, we include the dispersion, linear dispersion term here. Usually, modified Camassa equation has not linear dispersion, but I include here the linear dispersion term. Now, P-con solution exists when kappa is equal to 0, the form. Of course, this solution is a weak solution, not classical. Okay? So recently, I obtained the soliton, general soliton solution of the system here. This is an expression of one soliton solution like this. Okay. Now, smooth soliton exists when kappa k, parameter kappa k lie in the range there, 1 over square root 2, and a singular soliton exists in the range of parameters. So, this is the transition to smooth soliton to p-cons. But p-con limit of soliton solution, I fix the velocity of soliton 2. So, dash curve here is smooth, and when kappa k is 1 over square 2 is a solid curve here. Solid curve is the critical value of between smooth and singular soliton. But this Holm looks like a p-con, but the analysis shows that this is not p-con indeed. Then, if the parameter is 0.8, for example, the solution becomes singular. This is actually this is a 3-value function like this. So, my conclusion is that the p-con solution here cannot be obtained from the smooth soliton by any limiting procedure. But I have no idea about this. Now, I conclude my lecture by short summary. Direct method has been developed for conducting soliton solution of the Camassa-Holm 2 system. The property of soliton solution has been investigated in detail. Reduction of the shift system to the Camassa-Holm and Hunter-Saxton 2 equation has been demonstrated. Smooth soliton of the modified Camassa-Holm equation do not recover p-cons in any limiting procedure. A part of my talk will be detailed in the recent paper in Journal Physics 8. Thank you for your attention.
Thank you very much. You don't have any answer to your mystery or why you cannot have this transition. So, okay, maybe we can get some help from the audience.
So even
okay, please.
You discussed the limited case for the soliton for the modified Camassa-Holm equations, kappa k goes to 1, then kappa goes 0.
Yes,
but what about, is it possible you can just see what happens that kappa, just kappa goes 0 and the wave number is fixed. So that case is still
not wave number, because kappa k we must take kappa k 10 to 1, so that the k, when I take kappa to 0, then k yes.
What about the
yes.
0 case? I mean the smooth solution to.
Okay. Here is the parametric form of the one soliton solution.
Right. Smooth
so
soliton to
you said that if one takes the kappa 10 to 0 here in this expression, okay, but I have nothing maybe because this expression becomes 0 when kappa 10 to 0. If I k fixed, if I keeping k constant value and then take the limit of kappa 10 to 0, this becomes 0, and also this term divergent. Kappa is here, And also, velocity becomes 0 in the limit of kappa 0. So that's
for that smooth soliton, do you think it's any possible to get some other smooth soliton in that region? I mean, the kappa k between 0 and 1 over square root 2. That not that solution. I mean, is there maybe some other smooth soliton?
Do you know?
I don't know. That's up to you. But that's why you said obviously the kappa goes 0 is the 0 solution. It's the triple solution.
But usually you don't have that many.
Of course, this is very curious because Camassa-Holm and DP and Novikov, the smooth recovers P-con solution. But only this equation does not recover P-con. I have no idea about this.
Yes, please.
So briefly, I mean, can you have rho 0 positive but kappa equals 0?
Yes.
So what is, I mean, the CH2 system?
Yeah, which is modified?
No, the Camassa-Holm 2. The two components.
Camassa-Holm 2.
Yeah, if kappa equals 0 but rho 0 is positive. So this case, is it a...
No, in the case of Camassa-Holm, the zero bound condition imposed in the Camassa-Holm case. The Novikov case, non-zero bound condition, use 0. Two component Camassa-Holm?
Yeah, for the two components, my question is,
okay.
if kappa is 0 there and rho 0 positive, what is the specific of this case?
Yes, similar to, which is similar to the non-zero kappa case, similar to, okay.
Yeah, okay, thanks. So there is nothing. Okay, thanks.
Yes, please.
Is it possible to do something like this for periodic?
In the framework of the bilinear methods, it may be possible to obtain one-phase solution. May be possible because it simply obtain. But in this case, the tau function is expressed by an infinite series, not the final. Okay. Maybe very simple. Once because we have a system bilinear equation. Okay. But the general case will be very difficult to read. Okay.
There is time for one more short question. Can you indicate what or speculate? What is the misrepresentation of the physics when you have these conflicts? You model some physics.
Which equation you are interested in? Which equation?
Yes.
Which equation?
Which one? Yeah. Well, okay. To your mystery, where you have this, you cannot have this transfer from the continuous to the pickup.
In the case of modified
Yes. What is the misrepresentation of the physics in that equation? Can you speculate what?
But I have no idea.
I think maybe you think this way because you have started Green-Naghdi. Green-Naghdi equation system has physical the model, yeah. Then start that one that can derive the similar whatever the model approximations, the models like this kind of equations. So that's maybe the start point of Green-Naghdi system, and also the high order Green-Naghdi system that divided by the professional model.
You said there is no physical derivation.
For the
apparently
For the cubic one, there is no much physics. I mean,
modified is not so clear. I mean, the modified Camassa-Holm equation is not so clear. But for Camassa-Holm, because propagation equation for sure, the edge constant, they did something that justifications for the Green-Naghdi and back to the Euler equations here.
Do you know whether the
I like that comment. But I think maybe we are right on time, so we can stop here and continue this discussion over lunch. So thank you very much.
Thank you.